Imagine trying to fit a skyscraper into a phone booth. I mean, that is exactly what it feels like when you take a state-of-the-art 70 billion parameter language model and try to cram it onto an edge device.
Oh, absolutely. It's a logistical nightmare.
Right. And as machine learning practitioners, you know the standard scaling playbook intimately by now. You want lower loss,
Yeah.
higher reasoning capabilities. You just expand the parameter count, shovel in trillions of tokens, and throw massive compute clusters at the problem.
Which works beautifully in a data center.
Exactly.
Yeah.
But the moment you target edge deployments where, memory constraints are absolutely static and thermal limits are totally unforgiving, that brute force scaling playbook just hits a brick wall.
Yeah, the field has relied on the scaling laws for fixed depth transformers for years now. And they are incredibly reliable, but they are also fundamentally tied to expanding the memory footprint.
Which you just can't do on a phone.
Right. When you cannot physically add more parameters to a local device, you are forced to look for alternative orthogonal axes of scaling. And that search almost inevitably leads to the notoriously difficult territory of layer-looped models.
Yeah, and the premise of looped architectures, it sounds like a silver bullet for edge deployment. Instead of stacking, say, 96 transformer blocks linearly, you instantiate a single block of layers and iteratively recycle your activations through that exact same block multiple times.
You dramatically increase the available floating point operations, the FLOPs, without adding a single parameter to your memory footprint.
Which is the holy grail, right?
It is the holy grail for a memory-constrained device. You trade flexible compute cycles for higher reasoning capability. But historically, actually, training these layer loop models has been fraught with severe instability.
They just break.
Yeah, they are incredibly difficult to optimize and tend to diverge spectacularly mid-training.
And that instability is the core target of today's deep dive. We are exploring a highly technical paper titled Parcae, Scaling Laws for Stable Looped Language Models. The authors here, they bypass the usual empirical hacks and band-aids.
They do. They recast the entire looping mechanism as a nonlinear time-variant dynamical system.
Which is a mouthful.
It is, but by applying classic control theory, they structurally stabilize the architecture, which finally allows them to establish a unified scaling law for layer looping.
Okay, let's unpack this. Before we get to the mathematical cure Parcae introduces, I want to make sure we have a really vivid picture of the disease. What exactly is failing in these older looped models?
To map out the failure mode, we should first visualize the architecture, a standard middle looped model. It's frequently called a recurrent depth model. It basically operates in 3 stages.
Okay, walk us through them.
First, the model takes your input tokens and passes them through a prelude unit, projecting them into an initial embedding space. That initial embedding is then handed off to the recurrent unit. This is the core engine, where the hidden state is iteratively updated through the same transformer block for a set number of loops.
Got it.
And finally, after those loops conclude, the final hidden state is pushed through a coda unit to generate the vocabulary probability distribution.
That structural flow makes complete sense. But when researchers have tried scaling these recurrent depth models in the past, the metrics show the hidden embedding norm, specifically the L2 norm of the state, after all those recurrences, it just explodes.
Yes.
The loss spikes, the gradients completely shatter, and the model diverges.
The signal amplification becomes totally unconstrained. And prior attempts to prevent this explosion, they leaned really heavily on brute force normalization.
Like what?
Well, researchers would apply a combination of pre-norm and post-norm directly inside the transformer block. They were essentially trying to compress the residual stream forcefully to just, keep it bounded.
But that feels like treating a symptom rather than the underlying disease, doesn't it? I mean, it reminds me of an audio feedback loop.
Oh, that's a good comparison.
Right. If you place a microphone too close to a live speaker, the sound signal loops back into the mic, compounding on every single pass until the amplifier just blows out. Slapping aggressive layer norms on the residual stream, that seems the equivalent of just turning down the master volume on the amp.
It doesn't actually stop the feedback loop from generating.
Exactly. It only delays the inevitable blowout.
What's fascinating here is that the audio feedback loop is a remarkably accurate way to visualize the problem. The researchers behind Parcae realized that treating this purely as a deep learning optimization problem was a dead end.
They had to go deeper.
They needed to formalize that feedback loop mathematically, which led them to their core contribution, recasting the forward pass over the residual stream as a discrete, linear time invariant system, or an LTI system.
Okay, I am looking at this linearization step in their methodology, and I have to admit I'm a bit skeptical. To model this as an LTI system, They temporarily drop the actual nonlinear transformer block, the multi-head attention, and the MLTs from their state equations.
Mhm.
If we strip away the nonlinear processing, aren't we throwing away the actual brain of the model just to make the math easier to analyze?
It seems counterintuitive, I'll give you that. But
Yeah.
linearization is a classic, powerful diagnostic tool in control theory.
Okay.
Think of the state update happening in the loop as a combination of three distinct forces. You have the prior hidden state being carried forward, you have the fresh input embedding from the prelude unit being injected, and you have the complex nonlinear processing of the transformer block.
Right, the brain part.
Exactly. By isolating the first two linear forces, the authors could isolate the structural foundation of the feedback loop. They wanted to see if the architectural plumbing itself was inherently unstable, regardless of what the attention mechanism was trying to learn.
Okay, so if we isolate the linear components, the architecture basically comes down to two transition matrices. We have one matrix dictating how the prior state decays or grows, and another matrix dictating how the fresh input is continuously injected into the stream.
And classical control theory gives us strict mathematical boundaries for a system like that.
Which are?
For a discrete LTI system to be mathematically stable, meaning its state eventually converges to a bounded limit rather than blowing up to infinity, the transition matrix governing the prior state must have a spectral norm strictly less than 1.
Let's ground that concept of a spectral norm being less than 1.
Yeah.
It makes me think of the shock absorbers on a car hitting a pothole.
Okay, I follow.
The bump is the input signal. If the shock absorber is underlying physics, its spectral norm is exactly 1. It just passes that kinetic energy along infinitely.
Yeah.
The car never stops bouncing. If the spectral norm is greater than 1, the shock absorber actually amplifies the bump. The energy compounds recursively, and the car flips over. But if the spectral norm is strictly less than 1, the shock absorber acts as a dampener. It absorbs the energy, the bounce decays exponentially, and the ride smooths out.
The dampener analogy captures the exact mechanism. Now, apply that back to the prior looped architectures. When the authors analyzed how previous models injected the input embedding into the residual stream, they found the architectural designs fundamentally acted like shock absorbers guaranteed to flip the car.
Wait, really? How?
For instance, many models injected the input via simple mathematical addition. By simply adding the prior state and the input, the transition matrix governing the prior state effectively becomes the identity matrix.
Oh, and the spectral norm of an identity matrix is exactly 1.
Precisely.
So it offers zero dampening. It sits right on the mathematical edge of oscillation, completely vulnerable to any noise introduced by the nonlinear transformer block.
And it gets worse. Other architectures used concatenation with the projection layer to merge the input and the hidden state. That creates an unbounded, full-rank, real matrix. Its spectral norm can easily drift well above 1.
So it's actively amplifying the noise.
Yeah. When the researchers empirically tracked the spectral radius of these transition matrices during divergent training runs of older models, they consistently found the model's learning parameterizations where the norm exceeded 1. The state explosion wasn't an unfortunate optimization bug. It was a mathematical certainty baked into the architecture.
Here's where it gets really interesting. Identifying that the spectral norm needs to be less than 1 is great in theory. But how do you structurally enforce that constraint on a massive weight matrix during backpropagation?
It's tricky.
You can't just arbitrarily clip the eigenvalues at every training step. That would completely derail gradient descent and destroy the model's capacity to learn complex representations.
That is the exact engineering hurdle they cleared. They designed a specific architectural parameterization that structurally guarantees a spectral norm below unity without ever needing to clip gradients.
So how do they pull that off?
They start in continuous time. They define the transition matrix as a diagonal matrix of learnable parameters. But they don't just use the parameters directly. They take the mathematical exponential of those learnable parameters.
Ah, see the mechanism. Because the foundational property of an exponential function is that its output is always positive, regardless of whether the input parameter is negative or positive.
Then they explicitly attach a negative sign to that strictly positive output.
Okay.
Now they have a matrix guaranteed to consist of strictly negative continuous values. When they map this continuous system into discrete steps using a technique called a zero-order hold scheme, those strictly negative continuous values structurally map to discrete eigenvalues that sit firmly between 0 and 1.
That is brilliant. So by defining the matrix through a negative exponential, the gradient descent can adjust the learnable parameters all at once.
Exactly.
No matter how the optimizer updates the weights, the resulting discrete transition matrix is mathematically trapped with a spectral norm below 1. They built a structural dampener that the optimizer physically cannot break. The residual explosion is prevented by architectural design.
The structural dampener successfully stabilized the core recurrence. But the paper details another major hurdle. When the researchers scaled this stabilized architecture onto 1.3 billion parameters, they hit a late-stage instability wall.
Wait, it still broke,
Around 170,000 steps into training, the loss suddenly spiked again.
which had to be incredibly frustrating.
Oh, I'm sure it was.
But because they had built this LTI diagnostic framework, they didn't have to guess what went wrong. They acted like structural engineers, tracking the activation norms layer by layer to pinpoint the exact source of the stress fracture.
And the diagnostic revealed that their dampener was working perfectly. The spectral norm of the recurrent matrix remained totally stable. The nonlinear transformer blocks were behaving as well.
So what was spiking?
The massive variance causing the late-stage spike was actually coming from the matrix governing the fresh input injection. The output from the initial prelude block was simply injecting too much noise.
Ah, so the feedback loop itself was stable, but the initial signal being injected into the loop was just too loud for the dampener to absorb cleanly at scale.
The fix for that specific friction point was beautifully simple. They added a standard layer norm to the output of the prelude block right before it gets injected into the recurrent loop. Normalizing that initial injection completely eliminated the late-stage loss spikes.
Just slap a layer norm on it. That covers the architectural stabilization.
Yeah.
But the authors also highlight a major algorithmic bottleneck in how these models are trained, right?
Yes.
Because if you want a loop model to generalize dynamically at test time, you can't just train it on a rigid static loop depth. You have to expose the model to a distribution of depths.
Previous methods handled this by sampling the loop depth per microbatch. An entire batch of sequences would run through the model for, say, 4 loops. Then the next batch might run for 12 loops.
That sounds like it would create absolute chaos for the optimizer. You'd have massive, wild variance in the gradient updates from batch to batch, which explains the historical loss spikes.
Precisely.
So Parcae shifts this to per-sequence depth sampling within a single batch. Every individual sequence in the batch gets its own independently sampled loop depth. That would smooth out the mathematical expectation of the depth distribution significantly.
It does.
But I have to ask about the compute efficiency there. If you have a batch where one sequence loops 3 times and another loops 10 times, doesn't that jagged tensor shape completely break standard matrix multiplication optimizations on modern GPUs?
It would severely bottleneck throughput if processed naively. To maintain compute efficiency, they employ a clever masking trick. The algorithm finds the maximum sampled depth assigned within the batch. Every sequence in that batch physically runs through the hardware for that maximum number of iterations, keeping the tensor shapes perfectly uniform.
Oh, I see.
However, for the sequences assigned a shorter depth, the model applies a mask that effectively freezes their hidden state updates once their specific target depth is reached. The gradients are computed smoothly and accurately across the distribution without sacrificing any batched hardware throughput.
So the transition matrix is structurally constrained to act as a dampener, the input injection is normalized to prevent overwhelming the loop, and the depth variance is smoothed out algorithmically without losing GPU efficiency.
You've got it.
And the paper notes these aren't fragile heuristics. By guaranteeing stability mathematically, Parcae entirely removes the need for hypersensitive tuning. It converges beautifully across a massive range of learning rates, where previous looped architectures would just shatter instantly.
From 2e-4 all the way up to 1e-3. With the system finally mathematically sound, the researchers could test the ultimate question. Does looping actually provide a viable scaling axis compared to standard fixed-depth transformers?
The downstream performance data is staggering. They trained a 1.3 billion parameter Parcae model on 100 billion tokens. It improved the core and core extended benchmarks by 2.99 and 1.18 points respectively over highly optimized parameter-matched fixed-depth baselines.
To contextualize that for edge deployment, the 1.3 billion parameter Parcae model achieved up to 87.5% of the relative quality of a standard transformer that is twice its size.
Wow.
You are capturing the reasoning capabilities of a 2.6 billion parameter model, but only forcing the edge device to hold 1.3 billion parameters in its static memory.
That directly addresses the skyscraper and the phone booth problem. But it leads to a critical question about resource allocation, which the authors tackle through isoflop analysis. Since FLOPs are the ultimate currency in machine learning, they mapped isoflop contours at both the 140 million and 370 million parameter scales.
They wanted to definitively answer, if you have a fixed compute budget, what is the optimal ratio of training on more data tokens versus looping the model more times?
So what does this all mean?
If we connect this to the bigger picture, the empirical power laws they derived here are profound. For a fixed compute budget, they found the optimal amount of looping, the mean recurrence, scales proportionally to the compute budget to the power of 0.40.
Okay.
Simultaneously, the optimal token count scales proportionally to the compute budget to the power of 0.78.
Those power laws prove we can no longer just rely on the two-dimensional playbook of scaling data and parameters. We now have a mathematically predictable third orthogonal axis for scaling compute. To train a truly compute-optimal model, you must scale your data and your loop depth in tandem according to those specific ratios.
Bringing this back to the practical implications for deployment, understanding how looping scales optimally during training naturally provokes another operational question. What happens when you shift a trained Parcae model to test time inference? If you train the model with a mean recurrence of 8 loops, can you just run it for 24 loops during inference to extract free intelligence?
The paper proved there is no such thing as free intelligence. While some early research on tiny synthetic reasoning tasks suggested models could generalize to almost infinite loops, that behavior completely breaks down for large-scale language modeling. Pushing an 8-loop trained model to 24 loops at inference yields heavily diminishing returns. The performance saturates.
It does saturate, but the researchers didn't just empirically observe the ceiling. They modeled the saturation curve mathematically. They discovered that test time scaling follows a highly predictable, unified functional form.
I don't want to get bogged down in reciting the formula, but the shape of the mathematics is fascinating. It takes the form of a saturating exponential decay curve. As you increase the number of loops during inference, the test time cross-entropy loss decays exponentially, but it eventually bottoms out at a hard, irreducible floor.
And here is where all the theoretical threads of the paper unify perfectly. The researchers found that this irreducible loss floor is entirely dictated by the training parameters. It exactly matches the predicted loss derived from that isoflop training power law we just discussed. Your test time performance ceiling is mathematically hard-coded by your training compute allocation.
And the decay rate, the speed at which your model hits that performance floor during inference, is completely dependent on the fraction of the training depth you were utilizing at test time. If you train deeper, it takes deeper inference loops to squeeze out the final drops of performance.
This unified scaling law is robust enough that the authors used it to predict the validation loss of completely unseen, held-out models operating at varying inference depths. The average error of those predictions was astonishingly low, sitting between 0.85% and 1.31%.
That is incredible precision. But the most profound takeaway for me is why the test time performance takes the shape of an exponential decay curve in the first place.
This raises an important question, and it brings us full circle to the LTI system. In classical control theory, a stable, discrete-time LTI system, one with a spectral radius structurally held below unity, like the dampener we discussed, is mathematically proven to converge to its fixed state exponentially. The exponential decay observed in the model's test time loss directly mirrors the exponential convergence of the dynamical dampener they engineered in the residual stream.
It's all connected.
The network architecture, the training stability, and the macroscopic inference scaling laws are all expressions of the exact same underlying mathematics.
It is a masterclass in applying rigorous control theory to deep learning optimization. By treating the residual stream as a dynamic system and structurally forcing the transition matrix to absorb instability rather than amplify it, Parcae transformed layer looping. It takes it from a chaotic, practically unusable experiment and turns it into a predictable, mathematically sound axis for scaling, an axis that fundamentally alters what we can deploy to hardware with static memory constraints.
It allows practitioners targeting the edge to trade available, flexible compute cycles for higher quality predictions, breaking the absolute reliance on parameter bloat.
It is a paradigm shift, but it leaves you, the listener, with a final, provocative operational challenge to think about. We now know definitively from the isoflop power laws that increasing the mean recurrence during training improves the overall quality and lowers that irreducible loss floor.
Yes.
But the unified inference law dictates that doing so forces the model to take significantly more steps at test time to actually reach that floor. The deeper you train, the heavier the inference burden becomes. Is there a future routing mechanism or perhaps an implicit differentiation technique that could successfully decouple this relationship?
That is the crucial next step. Imagine designing a system that achieves the structural stability and deep representation learning of massive loops during training, but learns to dynamically collapse, route around, or skip those steps during inference without sacrificing the acquired accuracy.
We have finally acquired the mathematical blueprint to build stable, predictable loop transformers. The foundation is poured, the dampeners are installed, and the structure is sound. The next frontier is figuring out how to make that structure operate with dynamic test time efficiency.